We are now going to consider the so-called Cauchy Riemann equations. They are a bit difficult to derive, but they are easy to use. So even if you don't follow the proofs, don't give up, because we are going to utilize these equations eventually, and it will be pretty easy for you to do that. Let's just use some notations. We write the partial derivative of a real function u with respect to x is often abbreviated in this way, u x index x. Similarly, if we have the partial derivative of u with respect to y, we write just u index y. Let us now consider a point x0, y0 in the xy plane. We recall that the partial derivative of a real function u with respect to x is just this limit. And we are taking this partial derivative in the point x0, y0 here. Similarly, we have this expression for the partial derivative of u with respect to y in the same point. Very similar to the above definition, but recall that here, instead of using delta x, we use delta y. Let us now consider a function, a complex function, f of z, which takes the same form as it did previously. We have a real part called u of xy, and this is a real function. And we have some imaginary part here, which also is a real function, and of x and y. And this variable set, the complex variable set, is just x plus I y. And set 0 is some fixed point in the complex plane as before, which is equal to x0 plus I y0. Now, we assume that the derivative of f at this point, set 0, this fixed point, exists. And recall the definition of the derivative. We are considering this function, and which is a function of delta set, and we are investigating this function when delta set goes to 0. Recall that delta set now is delta x plus I delta y. So what we can do now is to express this term by u and v and delta x and delta y. And this is maybe not too easy to see, but if you just use the definition of f in terms of u and y, you will see that it can be written in this form. This is a very general form for this expression, and we are going to consider two cases. You remember that in order for the limit to exist, we must have that delta set, when delta set goes to 0, we have a limit which is the same if we goes along the vertical line or the horizontal line. So let's start with the horizontal line. That is when delta y is equal to 0. And delta x is not necessarily 0. It's a positive or negative value which is approaching 0. Then this expression, by rearranging, we see that this expression can be written in this form. No, we don't have any delta y, so letting no delta x go to 0, we obtain the following. When delta z goes to 0, using the definition of the partial derivative, we see that this guy goes to the partial derivative of u with respect to x in the point x0, y0. And this guy will approach the partial derivative of v with respect to x in the same point. Well, let's now consider the case when we are approaching 0 from above along the vertical axis. That means that delta x is 0, and we use some arbitrary value of delta y. Then the above expression reduces to this expression. It's also fairly easy to see. Note that in this case we have some imaginary value in the denominator, and this is not very useful, so we multiply with I in the numerator and denominator. And here we have not this problem, as you can see. But when we are doing this, we see that we get this complex function. And letting delta x go to 0, we obtain the following. We obtain that this part goes to minus the partial derivative of u with respect to y, and this part goes to the partial derivative of v with respect to y. So what we have proven now is that if this limit exists, that the derivative of f with respect to z in the point z0 exists, then we have two expressions for this limit. And these two expressions must of course be the same. So we have to conclude that the partial derivative of u with respect to x should be equal to the partial derivative of v with respect to y. And that the partial derivative of v with respect to x should be equal to minus the partial derivative of u with respect to x. And what I said now is the so-called Cauchy Riemann equations. We have proven parts of the following theorem. Suppose that the function f of x is on this form, standard form, and that the derivative of f exists in the point z0. Then the first order partial derivatives exists at x0, y0, and the Cauchy Riemann equations hold. That is what I now said, that ux is equal to vy and uy is equal to minus vx. And we also have seen that this must mean that the derivative of f at this point is just equal to ux plus I vx. These Cauchy Riemann equations can be used to show differentiability of certain functions. Let's now use the Cauchy Riemann equations to prove that this function is not differentiable at z different from 0. We note that the absolute value of z square is just equal to this guy, and this is just a real function, so the imaginary part must be equal to 0. So taking the derivative of u with respect to x, we get that this is ux is equal to 2x. The derivative of u with respect to y is also 2y, is similar to the derivative in x direction, and the derivative of v with respect to x is 0, and the same in the y direction. So in order to have the Cauchy Riemann equations fulfilled, we must have the following: 2x must be equal to 0 and 2y must be equal to 0. So the above theorem implies that the derivative does not exist when z is different from 0. Because in that case, x in the case z equal to 0, then x and y must also be equal to 0. So then the Cauchy Riemann equations are fulfilled. Here is another task which is possible to solve using the same equations. Show that the function f of z equal to the real value of z is not differentiable. So the function f of z equal to the real value of z is just equal to x. Z is just x plus I y, but in this case we are just using the real part of it. So this must be equal, u must be equal to x and v must be equal to 0. Using the Cauchy Riemann equations, we obtain easily the following, and in order to have the Cauchy Riemann equations fulfilled, we must have that 1 is equal to 0, and 0 equal to 0 is of course fulfilled, but this is not possible. So therefore f of z is not differentiable at any point. We can do the same also for the imaginary part of z. Exactly the same argument, and we conclude that this function can also not be differentiable.